Study Unit 6, Lecture 5. This lecture expands on three-phase fully controlled converters and specifically focuses on three-phase fully controlled full-wave converters. So shown in this diagram is a three-phase fully controlled full-wave converter. It bears a lot of similarity to the half-wave converter, except now all the semiconductor devices are thyristors instead of being half thyristors and half diodes. So the output voltage of this fully controlled full-wave rectifier is given by the following equation. V out is equal to 3 over pi multiplied by the integral from alpha plus pi over 6 to alpha plus pi over 2 of the sinusoid which is being fed into the bridge, which is root 3 multiplied by root 2v sine omega t d omega t, and solving this integral gives the output voltage as 2,34 cos alpha, where alpha is larger than 0 but less than 2 pi over 3. When compared to the half-wave rectifier, the output voltage of the full-wave rectifier is approximately twice that of the half-wave design. What should be noted for this configuration is that for a purely resistive load, the output voltage must be modified slightly and is given by 3 multiplied by root 3 divided by pi multiplied by root 2v 1 plus cos alpha of pi over 6, and here alpha is restricted to pi over 3 and 2 pi over 3. As before, the output voltage is a strong function of the delay angle alpha. So shown on the diagram here is the output waveform, or rather the output voltage, for different delay angles. When the delay angle is 0 degrees, then the pulses are quite close to each other and the output voltage average is quite high. As the output, or rather as the delay angle increases, these pulses become further and further apart, and eventually when the pulses are 90 degrees or pi over 2, then the pulses are very short and almost triangular in nature. It can be seen that for delay angles which are less than 60 degrees or pi over 3, then the output is continuous because there is no zero voltage. Or rather, it approaches zero but then immediately increases again. For larger delay angles, there is actually a period where the output will drop to 0 volts. At this boundary condition, where the output voltage will drop to 0, if the load is purely resistive, then the circuit will operate in the discontinuous mode. If there is an inductive load or some kind of back EMF, then the operation may be continuous. For this delay angle over here of 90 degrees, regardless of what type of load is present in the circle, the operation will always be discontinuous. And before moving on, it should be noticed, or rather noted, that for small delay angles, the ripple rate is 3 times the frequency of the actual supply frequency. So if, for example, was a 60 Hz supply, then the ripple present on the DC output would be 180 Hz. Once again, this is because there are effectively 3 supplies which are out of phase with each other, which contribute to the output voltage. So a note on highly inductive loads where there is a constant load current. As the output voltage approaches the maximum output voltage, the maximum output power will also be approached, and under this condition the delay angle alpha will approach 0. When the delay angle is 0, then the output current waveform as well as the output voltage waveform are in phase. This is why power is maximized. As alpha is increased, then the current output waveform and the voltage output waveform will start to become out of phase by the delay angle alpha. So as alpha increases, the output power will decrease. What this causes is that the reactive input power will increase, but the real output power will continue to decrease. So this will continue until alpha reaches pi over 2, and then the output voltage will be 0. At this point, when the output voltage is equal to 0, then all the power being delivered to the load is only reactive power, and there is no real power being delivered to the inductive load. If alpha were to be increased beyond pi over 2, then the polarity of the output would invert and there would be a negative voltage forming at the output. As this negative voltage increases, then the real power delivered to the load will also start to increase. Finally, this lecture is going to have a look at a three-phase fully controlled full-wave converter which has a freewheeling diode in shunt with the load. So the primary function of the freewheeling diode which is in shunt with the load is to prevent the output voltage from going negative and a power inversion from occurring. Or simply put, the diode allows current to only flow in one direction and thus develop a voltage of a certain polarity. If an inverting circuit was desired, then the polarity of the diode could simply be changed, and then this would prevent the converter from generating positive voltages, but it would be able to generate negative voltages. So to quickly recap, if alpha is less than pi over 3, then the output voltage is always going to be larger than 0. In other words, the freewheeling diode does not come into play for small delay angles. So for cases where alpha is larger than pi over 3 but less than 2 pi over 3, the output voltage with the freewheeling diode is simply V out equal to 3 multiplied by square root of 3 divided by pi times root 2 times V times 1 plus cos alpha plus pi over 3. What this means graphically is that for some small alpha, as in diagram B over here, the output voltage never truly drops to 0 volts and the output current remains more or less constant. For a larger delay angle with the freewheeling diode present, the output voltage will decrease to some value 0, but it will not decrease below 0 volts, as was the case for circuits where the freewheeling diode was absent. And that concludes this lecture.